In the diagram below, M1 is 1,000 kilograms, M2 is 2,000 kilograms, and M3 is 3,000 kilograms. We want to find what's called the total gravitational field at the position of M3. All right, so gravity, as we've seen in the past, is an attractive force. It's something that normally pulls objects down toward Earth. In this case, we're going to deal with 3-point masses, so there's no Earth in question. It's just going to be an interaction between these three masses, as if they were the only thing in space. So it's a little different. Now, the way it works is M3 is going to be simultaneously attracted to M2 and M1. So there'll be two vectors on there. All right, so we could give those names. They could be forces. So this could be the force of gravity of 1 on 3. So you say what type of interaction it is, and then you say what object is acting on what object. Then over here we would have Fg 2 on 3. Okay, but those are gravitational forces. We also have an idea called a gravitational field. And there's just a subtle difference between the two concepts. So I'll show the differences. We're still going to have vectors for our gravitational field, which point the same way as the force vectors. But they are not forces. They are going to be in the units of meters per second squared. They are acceleration units. So we can call it A due to M1 and A due to M2. All right, so they're going to be vectors, and we want to add them as vectors to get the total. Because right now, these are just two individual contributions to the total field. So when we get the total field, what we want to do is add them together into one big vector. And so that vector might look something like this. Okay, because it is a vector sum of those two. And the way you sum them is through the head to tail method, or like a parallelogram method it's called. That's where you got one vector pointing one way, another vector pointing another way, and you take one vector and put its tail on the head of the other, or you could take the other vector and put its tail on the head of the first vector. Either way, you arrive at the same point. And if you just draw a final result from the tails to the heads there, then that is what would be referred to as the total gravitational field. All right, so what's the formula for gravitational field? Here it is. It will be A equals negative G M over R squared R hat. So there's a lot to it. And we'll go over what each of the different things mean. So G is the gravitational constant, it's called, which is 6.67 times 10 to the minus 11. Units are Newton meters squared per kilogram squared. So they're designed to work with the other quantities in this formula in order to make acceleration units. All right, so that's something that's in the formula sheets there, that gravitational constant. It's important to know that the m is the mass exerting the field, though. It's not the mass that's feeling the field. Like, it's not the mass that's in the field. So see, m3 is considered in this problem to be in the field. Like, it's feeling pulled by these other two. And because of that, we want to use the other masses in our formula. All right, so r is the distance, the radial distance from one mass to the one that's feeling the field. And then r hat is a tricky thing. I'll draw what r hat is. All right, so r hat points from the masses exerting the field toward the mass where we're trying to evaluate the field. These are r hat vectors, they're called. So one of them is r hat 1, this one could be r hat 2. All right, now let's set it up. Our total acceleration, our total gravitational field, is going to be a combination of the vector sum of A due to mass 1 plus A due to mass 2. So we just want to sub in the formula here. Negative G M1 over R1 hat. And then we square the denominator. So that takes care of the first contribution. And then over here we want to use the second contribution. And it'll look like that. That's how it would always be for two masses exerting a field on some point in space. Notice that I didn't even use M3 at all in the calculation. It doesn't matter what mass is in the field. The gravitational field is just a property of the masses around that point and like their geometry and relationship to that point. Alright, so how do we plug in? 6.67 times 10 to the minus 11 M1 was stated to be 1,000 kilograms. Alright, then we'll divide. Okay, so we got to get the physical distance between M1 and M3. Alright, so how far apart are they? Well, if you do a little Pythagorean theorem, a little triangle there, you'll see that the height is 4, width is 4, and if you do it, you'll find this is 4 radical 2. So, you just do 4 squared plus 4 squared equals R1 squared, because this is R1. And then you square root, and you get 4 radical 2 is R1. So we just want to put that in for our radius. And we will square that. Now the hardest part. We have to substitute in something for R1 hat. Alright, so how exactly do you do that? Well, we have a formula for it. And R hat is a unit vector, which means it has a length of 1. And what we're going to use then is we're going to use this. Cosine theta I plus sine theta j. So theta refers to the angle in standard position between M1 and M3. All right, so what do I mean by that? I mean that if you draw this line here, the angle that it makes is the theta in standard position there. All right, so just to be totally clear as can be, redraw it for a second. When we draw a vector from M1 to M3, we're drawing a position vector, R1. And see how it points from M1 to M3. So what R hat is just a unit vector which points in that same direction. And that can be R1 hat. It doesn't have the same length, though, as R1. R1 has a length of 4 radical 2. But R hat just has a length of 1. Alright, so whereas R1 would be given by 4I plus 4J, R1 hat is simply cosine 45 degrees I plus sine 45 degrees J. You can see why it's 45 because, you know, the x component and the y component are both 4. So this is a 45 degree angle. Alright, so what do we get for R1 hat if we do that? We get R1 hat equals radical 2 over 2I plus radical 2 over 2J. So it's just like a scaled down version of the original R vector. But anyway, that is what we want to plug into our formula. Alright, that takes care of M1. M2 is easier. You just need 6.67 times 10 to the minus 11. It's 2,000 kilogram mass. Now the distance. The distance between M2 and M3 is 4. So that's what we put in the denominator. Now what about its R hat? Well, that points from M2 toward M3. It's R2 hat. And that one's actually much easier. That one can simply be called I hat. Because remember, our hat vector is a unit vector, so it has a length of 1, and I hat has a length of 1 too. And it just points to the right in the positive x direction. So that's super easy. Just put an I hat on there. Alright, that's the setup. All we gotta do is just calculate it all. I'm getting negative 2.08 4 times 10 to the minus 9. That'll be newtons per kilogram will be the units. And then we'll multiply by radical 2 over 2I plus radical 2 over 2J. This one I'm getting 8.338 times 10 to the minus 9. Yeah, alright, that looks pretty good. So I'm going to distribute this to both of those. And I'm getting 1.4 7. Alright, now we can do the last step, which would be to combine the like terms. These are both x direction components, so we should combine them. Looks like negative 9.812 times 10 to the minus 9 newtons per kilogram I minus 1.474 times 10 to the minus 9 newtons per kilogram J. That would be the total gravitational field, it's called, at M3. Alright, so as you can see, according to the components, like it does point in the third quadrant, which is what we wanted according to our picture. I mean, it does say you can put it in IJ notation, or you could put it in component form. Or you could do an angle and a magnitude. So let's look at the next question, the next part of it though, which says to go on and find the force. So here we want to find the resultant gravitational force that acts on M3. So gravitational force has a similar formula to acceleration. The formula is Fg equals negative G M1, I'll put M3 over R13 squared R13 hat. That would be the formula we could use to find the force between two masses. As you can see, now it includes both a M1 and a M3. Okay, so that would be the force of gravity, I should say 1 on 3. But you could also have a force of gravity of 2 on 3. See, they both can contribute. It's called superposition when they both contribute and we have to add them as vectors. So we would have this. The R13 just means the distance between 1 and 3. R23 means the distance between 2 and 3. Now we could go through that whole calculation if we wanted. Basically, it'd be very similar to the calculation we just did. But there is also this from the weight formula. Fg equals m times g, where g is called the gravitational field. M is the mass in the field. And this F is, of course, the force it feels. So in our problem, we would want to let the mass in the field be M3. That's the one that's feeling the force. According to our, analysis, that it's being pulled by M1 and M2. In all reality, they're all pulling on each other, so it's just all relative, but right now we're just choosing to make M3 our system. Alright, so I'm going to use this formula here to take all the work that I had just done and not have to redo it. All we got to do is say that Fg on 3 is going to be the mass of 3, which was 3,000 kilograms if you look back at the problem. And then we want to multiply by our gravitational field vector. I'll do it in IJ notation. We want to multiply by the negative 9.812 times 10 to the minus 9I minus 1.474 times 10 to the minus 9J. Alright, so see here, G is A. They're both an expression of the gravitational field. Alright, so let's see what we get. .94 times 10 to the minus 5 newtons. That needs to be negative. And then minus 4.42 times 10 to the minus 6 newtons J. There's our gravitational force.